Hey, what's going on, guys? Komaki Games here. In this video, I'd like to present a KIM-1 emulator running on Arduino Nano. We'll talk about the project origins and how exactly this was possible to be achieved later on. But first, let me demonstrate how the actual emulator is actually working. So for those of you who's not familiar with what the heck KIM-1 is, so KIM stands for Keyboard Input Monitor, and this is the computer that was released back in 1976 by MOS Technology, just a couple of years after releasing their legendary 6502 processor. So KIM-1 was a single board computer intended to give an opportunity to hobbyists and engineers to play around with this newly created chip, which made the revolution in home PCs basically. All of this stuff we have now has actually started back from then, right? So what I love KIM-1 for is the extreme minimalism it introduces when it comes to manipulating the memory by inputting machine codes directly into the memory and allowing the user to work with those, to run the code and even to see the output. So the entire display of the original KIM-1 actually consists of this 4 digits on the left and 2 digits on the right. So the first 4 digits represents the address we're currently at, and the second 2 digits represent the value that we have at this particular address. So this is the bare minimum version of a hex monitor or hex editor, call it however you want, that actually allows us to do two most essential things: to inspect memory locations by entering the address, and also it allows us to change the values in the memory. And that's how we can input 6502 machine codes into this emulator, and then we can run it and see the output. So let me start the demonstration from simply inspecting a certain memory address. So if I say 0, it's 1. Okay, so if I say 0010, I'm not still that clear with the keyboard layout. I have a cheat sheet right over in here. Just not sure if it's seen. Yeah, so here is my cheat sheet. All right. So here we have, now we are inspecting the memory location hexadecimal 10, which has the value of 10. And apart from actually inputting the address from the keyboard, so we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 A, B, C, D, E, F buttons, and these buttons are control buttons. So this runs the program from the current memory location. This goes to addressing mode. This button allows to change the value of the given address. This one makes increments memory address we're inspecting by 1, and this one loads the program counter to whatever location we currently have, and it's more like used for debugging purposes. And this one is reset. I don't have a single step switch here, and also I don't have the button to stop the execution. So instead I would just be relying on reset, which is not the best ever way of doing things, but anyway, just don't have enough buttons. So, but that's okay. So if we press this, this button, up button, is known as the plus button on the original KIM-1. And when I get done with this demonstration on the real hardware, I'll demonstrate how the KIM-1 keyboard and original KIM-1 keyboard and display actually looks like. But for now, I just want to demonstrate that here we can increment memory locations by 1, and that's pretty how it works. So let's drop back to 0000, and now what if we want to input the value? So say we want to put some sort of a value. In this case, I need to go to data entering mode, and for instance, I want to set the value of DE, right? And then if I say next, like increment instruction, I'm still in the mode of entering data, And for instance, I can input another byte like this. Not exactly what I wanted, but that's okay. So I can actually say like this. All right. And I can then go further on, but let me just go back. Okay, I can't go back because I'm still in the data mode, entering the data. So here I press left to go back to the addressing mode, and now I can inspect the address of 0000 and 0001, and those bytes that we have just input there to those bytes. But actually, I want to get rid of those for a while, so just reset these bytes back to their initial values. Right, and now going back to address entry mode, and now the addresses we're interested in are 0010, which has the value of 10, and 0011, which has the value of 11. And now we're going to be running a program that is bundled into this emulator by default. And the program is from the legendary so-called book of the first book of KIM, which was the manual for users to type in machine code listings from the book just right directly into their KIM-1 and see the output. So the program that we're currently going to be running, what it's going to do is going to swap the memory locations in addresses 0010 and 0011. So here in the address 0011 there would be 10, while in the address 0010 we'll have the value of 11 here. I know it doesn't look that fascinating apparently, but let me just demonstrate how this works. If I say 0020, no, it's not like this, 0200, I need 200 hexadecimal. And here we have the very first byte of our program. So let's list the program like this. So there are a few bytes. I'm not going to be diving into what exactly they are doing. Well, they literally just loading the values to the A and X register from the hexadecimal values 10 and 11, and then swap them using the STA and STX instruction. And it should normally terminate here, right? So now let's drop back to 0200. And now in order to run the program, I need to, so in my case, this should be select. Okay, so we did finish with the address 020A, which is correct. And now if we go to 0010, you see, like, we already have the value of 11 here, while previously we had the value of 10. And here we have the value of 10 instead of having the value of 11. So, which means that our program has just worked perfectly well. But you might be wondering that it's like not very serious and things like that. So the author of this project, I'm not the author of this project, I've just adopted this project to run on on the hardware that I have, this LCD Shield, while the original version was running. I was displaying like trying to mimic the original KIM-1, displaying the data on the LED using the LEDs, the six 7-segment LEDs. Well, actually, he used 8 7-segment LEDs, but that doesn't matter. And he had a custom keyboard as well. Not a keypad like I do, but anyway, the idea is fairly the same. And what he did, he did add a couple of ROMs, like several ROMs, up to 4 if I'm not mistaken, including Hex Monitor by Steve Wozniak that was running on Apple One. He added the MicroChess by Peter Jennings and the Assembler by Steve Wozniak and someone another guy, I don't remember his name. And something else. Yeah, floating point number library, if I'm not mistaken. Yeah, so quite plenty amount of ROMs that are kind of bundled into this computer. I'm still playing around with this, and I'm still learning how to use all of this stuff. So what I can show you guys for now is how chess works. So let me reset my CodeMonkey KIM. CodeMonkey KIM works on CodeMonkey KIM This is cool, right? And at the address of C0000, we have the ROM for our MicroChess by Peter Jennings. And if I just say select here, it now actually starts the program, and nothing yet happens on the display. However, I'm currently looking at my serial monitor that is running on my laptop, and there I see that the chessboard has just been printed on the screen, and now I need to reset. Set the new game, press C, and now I have the board being initialized. You don't see this at the moment. So here you see this C, 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 and this is something related to the site to move, if I'm not mistaken. And I also see that line on my laptop. I'll demonstrate this from the laptop perspective as well, just right in the moment. But for now, in order to make a move, I need to press the PC button to kind of like set the program counter. And in my case, this is the button down. And now he just made a move, and you see this. So 0 is the side to move. So currently it's black to move. F is the piece that has just moved. He moved E2, E4, right? And 13 and 33 are the encoded coordinates for the source and the target squares. So if I now press the E button like this, now on my serial monitor, just swap the side, and now I can make it play. Now I make it thinking to make a move for the opposite side, and now it takes longer. So on the serial monitor, I have some dots being printed at the bottom of the screen. I'll show you how this works when I go to my screen sharing session here. Right, so yeah, he just output the move, and here is the point of the move, and again, like the source square, the target square, and this time he moved E7 to E5. So as you can see, so if I just had a chessboard right here, and if I had there is a documentation for MicroChess Lowen actually to see the mapping for the from square and to square, like to map all of the squares, so you can visually translate the squares like this coordinates to the board coordinates like E2, E4, etc. And then if you just have your chessboard somewhere near, and you just can move the pieces on the real board and play the game versus the computer, which is absolutely astonishing to my personal opinion. Well, okay, so I guess this is pretty much all I can show from the perspective of the hardware. And now let's inspect the project's origins and have a look how this sort of a thing looks like from the serial monitor perspective. And one more little thing, just before we end this demonstration. So let me adjust this slide a little bit. Yeah, I just reset, and I just want to show you another little trick, which I personally love so much. So here are my hands, right? I'm not touching the Komak Kim, but I will now be typing digits on my laptop on a keyboard. So say 0010, and you see, like, because of the serial connection, so currently my KIM-1 is actually connected to the laptop, and hence I can use the keyboard in order to manipulate my KIM-1. But that's not the official mode, let's say. While the official mode actually doesn't change the content of the LCD screen or of the LED segments that were used in the original model. But anyway, this might be quite handy to work like this way. And also bear in mind the fact that we have a ROM for a tiny assembler. This means that we can develop programs completely within this piece of hardware without even the need of a laptop. And what is even more cool, that the EEPROM in Arduino Nano, in my case in Arduino Nano, but literally in whatever Arduino that has EEPROM, I'm not sure if all of them have EEPROM or not. What you can do, you can actually mimic the cassette tape loading data from cassette tape and saving data to cassette tape using the EEPROM as the source for cassette tape data. And the author of this project did even provide a sort of a file system that you can maintain in the EEPROM. Well, a little bit of a downside of that is that you can actually you can write to EEPROM more than around 100,000 of times. But anyway, that's fairly big enough amount of attempts you can write to that EEPROM. And also EEPROM can even be used as RAM. So instead of running only 1K programs, you can even run 2K programs potentially on this computer. And also you can load the programs from the computer and save the programs like from the laptop via serial port, via USB in this case, and sending the data that you've entered here in this machine back to the laptop. Okay, so this is regarding the demonstration of the real hardware. Now let's have a look how this looks from the serial monitor perspective. Okay, so now let's have a look at exactly the same device, but from the serial monitor perspective. So I'm using PuTTY or PuTTY, call it however you want. And well, it works. There is a version for Windows as well. I'm on Linux. But anyway, I need to add the sudo command because otherwise I'm not going to be allowed to talk to my USB port. So here we go. And now just a few settings here. So I'm going to talk to serial port, and I know that my Arduino is connected to TTY USB 0 at 9600 baud speed, which is important. And also, just for video purposes, I want to make the font change, and this free mono would be fine in 24, just to make it kind of almost full screen. All right, so now I can say open, and here we go. So currently, there are two modes in this serial monitor. And the first mode, well, before I modified the code, it was kind of printing those 6 digits here. And this is the first mode allows to type the codes, to type the digits from my laptop, from the keyboard of my laptop. And meanwhile, that would be displayed on the LCD screen as I've just been demonstrating. So now if I say 0010, you can't see this, but trust me, on my display, it just shows currently the address of hexadecimal 10 and the value of 10 there. But here you can't see anything because I was horribly running out of program space, so I needed to disable the output for this 6 digits, and I use that actually for the LCD screen instead. But anyway, this is not the way. This is only needed for debugging and the so-called luxury mode, as they call it, for working with KIM-1 via serial port, was the following. So if I just press tab here, we're going to TTY mode, and here is actually the output that is on my screen. But if I now change this to something else, so if I say for instance 0000 and then space to enter this, now I'm inspecting the memory location of 00, and I can even write some data there at the moment. But on my LCD display, nothing is changing because I'm in this so-called TTY mode, and that's the way how the ROM of KIM-1 operates. So that's the exact behavior that we're supposed to be having. And just a few words regarding the history. So if one was rich enough back in the day, in the late 70s, he could have buy a terminal, a real terminal, like the display and the keyboard. And I'm not sure, it did cost around $1,000. If I'm not mistaken, I might be horribly wrong, but it's much. If the KIM-1 on its own costed $245 back in the day, so it was like much more expensive. I don't know whether it's comparable to how the laptop is more expensive as opposed to Arduino. Probably not that much, but anyway. What kind of idea do I want to give you here, guys? That here in the serial mode, we can do exactly the same things that we have been doing on the LCD screen just read a moment ago. So, for instance, here to the address of 0000, I want to input a value of, say, DE, and yeah, just type this in lowercase, hence it's not going to be working, I believe. 0000. Yeah, so I need to type this uppercase, and then I'm pressing dot and 0000 space, and now I have this byte being flashed into the memory, which is good. If I want to go to the next, if I want to increment the next, if I want to increment the address, I need just to press enter. It would be showing the next address. However, if I press space, it will be showing address 0. That's how it works. So let's just go and reset this back to 0000 and oh my god, space. Yeah, so now I did reset that, and we can still inspect, say, 0010 and the value that we have there, and then 0200 where the program that we've been running is located. And here we can see the bytes for this program, so from 200 hexadecimal and up to right over in here. So this is the program that swaps the values in the addresses hexadecimal 10 and hexadecimal 11. All right, but it's not the most fascinating, it's not the most interesting thing. So let's have a look how chess works. So if I say C000 space, and now if I say shift and G, yeah, here we have chess up and running. So now to reset, I need to say C. Okay, so now reset the stuff, and now in order to make it work, make it a move, I need to say shift P, if I'm not mistaken. Then that should be the case. Yeah, yeah. Sometimes no, it's actually this is actually okay. So yeah, let's say shift P, and it just made the move. Now, if I want to make, if I want computer playing versus itself, like I've been demonstrating on the LCD display, but that wasn't really that clear. So the only thing that is actually getting displayed on the LCD is this. And now, by the way, on my LCD display, I have this values being displayed. So that's what I have there, 0F, 13, 33. And now these numbers would make a better sense. So 0 stands for white to move. No, actually. Well, I'm not sure whether it's I'm not sure whether it's showing the site that has just moved or the site that is currently about to move. I'm not sure. And they're encoding for pieces. So this F stands for key and spawn. So there is entire user manual for MicroChess, and I'll provide all the links related to this, to KIM-1 in particular, and to MicroChess as well in the description below the video. But before that, so just to give you an idea, so 13, 33, so if say, so 10 and 3, so this is rank 10 and this is file 3, so we have 1, 3, which stands for 13. So from 13, this place goes to 33, so 3 and 3, it goes here. So now if I want to, so in order to make computer playing itself, I need to say E, which swaps the board. And if I say shift P one more time, it would now start thinking. So what I've been talking about, so this DA's been printed at the bottom of the screen, right? And then it just moves a piece after he's done. And then I'm not going to be playing the entire game because it takes ages to complete. And if you're interested how I'm playing versus this game, you can have a look at the video I made on my chess programming channel, where I'm more like focused on this chess program rather than the KIM-1. Right? But just to give you an idea how one can move pieces, so let's say we want to move the knight from G1 to F3. So first we need to enter the source square address of where this knight stands. So this is going to be 70, 76. So if I just say 76, and you see like this, here we have this 76, right? And then to where it goes to 5 and 5, to 55. So 5, 5, and then I need to say enter. I just hit enter, and it puts the 90 here. And in order to make the computer think, I need to say shift P one more time, and it actually starts searching for a best move from this position. So we'll now let it stop, and by the time it's thinking, let me go to here, CPU. I just want to find the addresses for some ROMs available. In particular, I'm interested in, yeah, here they are. So mini assembly, and I have no idea how to use this at the moment. I can just show you that it's kind of working. And also the famous monitor by Steve Wozniak that was working on Apple I computer. And probably we can even try to input the program from the Apple I manual. I didn't yet test this, so I can't say for sure that it's going to be working. But anyway, so I say Shift Q to escape back to the serial monitor, and now, no, I probably didn't escape. Well, anyway, let me just reset my Arduino. All right. Oh, I need to say tab, right? Okay, so back to this mode, and just to get an idea what kind of address. So let's start from FBAE. Okay, so FBAE, and here is the first byte of this tiny assembler. So if I say Shift and G, you see like it lists the instructions, or I don't know. Well, to be honest, I'm not sure how exactly. Yeah, probably it lists the program. So let's try to say LDI, for instance, the instant value of hexadecimal 10, for instance. So yeah, it actually. I'm not sure. I'm not sure how to use this. I really need to work around with this. Let's say STA to the address of 10, right? Yeah, probably it's given me some error, or maybe not, or maybe on the contrary, or I don't know. I really need to work with it. But the idea is that we can develop a program in 6502 assembly just right on this emulator. So in this case, I'm not using my laptop for developing. I'm using my laptop only as the teletyper. That's pretty much all about it. I only use the keyboard and the monitor to display the data, but that we do exchange by serial port. And this is really fascinating, to say at least. All right, so now let me demonstrate something I understand a little bit more. So again, let me just reset the Arduino, and by the time it's happening, I just want to have a look at Apple I manual, okay, and because I don't really remember how to operate this famous hex monitor by Steve Wozniak. All right, so here somewhere we have the program, the test program for Apple I. Was too far away. Yeah. This is pretty much all about it, I believe. So starting from location 0. I didn't run this. I'm not sure if it actually is going to be working, but we can give it a try. So the hex monitor by Steve Wozniak leaves at FF00. So let's go there. So FF00 and Shift G to start. And now we're already in this monitor. So for instance, if I say 0 and enter, I can see the whatever in 0, right? Say, I don't know, I can actually I can input like this as well, so it doesn't matter, it loads a different typing. And yeah, I don't remember by heart or by heart obviously how to input the data. So let's try this. So 0 and then the colon. So 0 colon. Maybe I should put this into a separate window just to inspect. Okay. So now it's much. Oh, whoa, hold on a sec. Can I make the browser always on top? probably not really. Okay, so in this case, should be fairly enough to like, so, oh, I just, okay. Yeah, I will know, so yeah, this hopefully would it be good enough? Yeah, so just to make it a bit bigger. So here is the program that we'll now try to enter here. So 0 colon and then A9 space B space 0 space B space AA space B. Oh, hold on a sec. Or well, actually, the original monitor didn't really load to. If I'm not mistaken, didn't load to take back, which is cool. So yeah, actually B stands for break, so it's literally enough to do like this: 0 AA 20 EF FF E8 8A 4C 2 and 0 for break, I believe, and hit enter. Well, I'm not sure actually, is this, yeah, let's try to see. So 0 dot A return. Okay, so here is the program. Well, probably, I'm just wondering, so A9B, oh no, A90, what the heck this B is. Okay guys, I'm sorry, let me just input this one more time. So 0 and A9 space 0 space AA space 20 space EF space FF space E8 space 8A space, probably because I was deleting using the backspace, 884C, and yeah, those characters probably were treated as the input because this hex monitor is not assuming that you can take erase the characters. Well, at least that's how it works on the Apple I emulator. Okay, so it's 4C and 2 and 0 and enter. All right, so now let's have a look. 0 dot and A and return. So here is the program. Okay, so this should print out on the display the program you have just entered, which it does. All right, and now we need to say R and run the program. And how it behaves on the original Apple I actually starts printing the ASCII characters and scrolling the screen in a never-ending mode. I have no idea if it's ever gonna be working here. It's a KIM-1 emulator. It's not the Apple I emulator, but again, like the 6502 is the same, so it's probably should be something like that. So, well, I have no idea, to be honest, so still need to make sure, like, I don't know. So let's try. So this I should say R and enter, and nothing happens. Yeah, for some reason nothing happens, but you know what, I'm just thinking, what if I go to 0 0 0 0. Yeah, so here is the program. Maybe if I just run it from here, so Shift G. Yeah, it kind of works. It doesn't work exactly as it should work. Doesn't work exactly how it works on Apple I, and neither the real Apple I or the emulator. And this particular PUTTY serial monitor behaves a bit odd, I believe. And I don't know, probably maybe I just made some mistake here. But anyway, what it does, it prints the entire ASCII character set, which is exactly what this program is intended to be doing, right? Now, I have no idea how to stop this, to be honest. Shift Q maybe, yeah, I don't know, and I don't even have the hardware reset button for like the stop button like on original KIM-1, so I just use reset instead. Okay, and yeah, now we're back, but yeah, actually our program has died after, but well, anyway, yeah, just really need to work this out. This is just the very initial implementation, so I really want to add more things like potentially print into LCD screens, so I could be making games like I did Chrome Dyno for my CMK computer. I have no idea how this is possible, you assume, in this kind of environment. I'm still pretty new to this environment, but I hope that should be possible somehow. Okay guys, so this is regarding the demonstration, but before we end, so yeah, just end the session here. Before we end with this video, the very last thing I want to demonstrate, yeah, so what I've changed in the source code. So yeah, I will give you a link to the original source code, and the source code I'm modifying is not yet available in public. It would be available when I just finish what I'm trying to do here, but what I've changed, like conceptually, Shift F, what have I done? Nope. Oh my god, yeah, like this. So Control F, and I'm looking for scan character. Nope, scan. Okay, what it scans? Oh, not in the CPU here. Scan character. Nope, scan key. Yeah. So here we had lots of code that was traversing the actual words intended to be on the circuit with this project I forked it from. But I'm just reading the keypad. Here I'm reading the keypad, and well, actually not only the keypad, but also, so I'm either reading the keypad or the buttons on the LCD shield, which are connected to the analog pin 1, analog pin 0. I'm sorry. And that's how I can, I'm using this for the command buttons, right? While the keypad, the 4x4 keys keypad, is used to enter the hexadecimal values from the keypad. And another interesting function is called drive LEDs, and this was initially what it was initially doing. It was just updating the LED 7 segment LEDs. But I just made it to actually print the values to the LCD screen instead in the hexadecimal. That's pretty much all about it, so nothing really special. And here in the CPU.c, so by the way, this is the famous 6502 emulator, which is called Fake 6502 by Mike Chambers. Yeah, all the links will be in the description below the video. So here, I've modified the code a little bit, so I just got rid of the code that was printing this 6 digits to the serial port, and instead I'm just printing them to the LED. So this is how it works. So not really that many changes to the source code. It was just I spent more time trying to figure out how the entire thing works. And to be honest, I'm extremely happy with how it works, and I love it so much. And there are lots of features still to explore, like storing data to EEPROM, which is possible here as well. So imagine you're working on this KIM-1 emulator outside of the laptop, so it's not connected to the laptop, it's just connected to the power supply. So say I've written some awesome program and made a video on that, and then I can save this to EEPROM, and if I power off my KIM-1 emulator and then I power up again, and then I would be able to load my program from EEPROM just like as if it was a cassette tape. And this is so fascinating. And also we can obviously load the programs via the serial monitor and store the programs via the serial monitor as well. However, I didn't yet try that, so to be honest, at this moment I have no idea how that is about to be done, but that should be possible. So hopefully the next upcoming videos are about to fulfill this gap. And now finally, the very last but not least, probably the most significant thing I'd like to share with you guys. So this is the original project. It's created by Oscar, oh my god, I forgot his last name. So his name is Oscar, and what he did, he has created this. So you see, like, it's based on Arduino Pro Mini, and here is the custom printed board. This 7-segment LEDs here, buttons, and eventually it looks like this. So these are the dreaded KIM-1. This is the dreaded KIM-1 display, and it's like, it's very tiny. It's really like a half of a modern smartphone, basically. And he has a video on YouTube somewhere. Initially, I saw a video how he works with this sort of a thing, and that was so fascinating, really. So you see, like, the original hardware was quite different from the hardware I was running this project on. So I needed to change the source code. It was handling this kind of hardware, and currently I'm pretty happy with what I have. And thankfully to Oscar, I can now enjoy not only KIM-1, but at some point Apple One. At some point, this might be, like, because we have the ROM for Apple One, this might be treated as Apple One at some point. And have the MicroChess to play, and even have the assembly. And oh my god, that's so fascinating. I don't know, guys. I'm feeling like the happiest man in the world, to be honest, because this is my dream computer, basically. So back in the day when I had ZX Spectrum, I had a horrible issues with uploading the data via the cassette tape, and if I could to load the data from the cassette tape, I had no idea how to write this, because I was 7 years old and nobody explained it to me, basically. So yeah, that was a bit of a pain. But now with this EEPROM, I can read and write data just being on board, okay? And I can develop programs just using my emulator and nothing else, and I can make videos on that as well. So hopefully after my journey with a SimK computer, where I've been creating the imagery processor, here we're finally back to 6502, and hopefully from now on there will be more content on how to code in 6502 assembly, as far as we have the hardware where we're going to be running this program. And by the way, according to Oscar, the author of this initial project, it's called KIM-1, by the way, for those of you who are unaware of this. I'll give a link to this link in the description below the video as well. So according to Oscar, the speed of how, let's say, MicroChess works on Arduino is exactly the same how it should be on, like, the real KIM-1. So it's apart from the cycle accurate 6502 emulator, it also seems to be like about the same speed, like, so like about the same power of the hardware, let's say. Even though, yeah, obviously the frequency, like the processor clock for, like, in Arduino is much faster as opposed to standard 6502 1 megahertz. But anyway, he said, like, from the speed perspective, it's pretty the same. I'm not sure how it works internally, to be honest, but anyway. So just wanted to share with you guys this dream computer I currently have, and I don't know. It's gonna be my birthday in half a month, probably somewhere like that, and I couldn't even imagine a better present than this sort of a thing. So yeah, this is it from my side. I hope you enjoyed the video. Thanks for watching. Until the next time, and take care.